For step 3, you want to compute the test statistic. For the chi-square one-way goodness of fit test, the test statistic is the chi-squared test statistic. It has this form, right? This is the chi-squared test statistic. Right? What it's doing is it tells us how far off our observed or actual distribution of counts is from some claimed or expected distribution of counts. Remember that capital O refers to our observed counts in our data. That capital letter E refers to the expected distribution of counts based on some claimed distribution in the population, and where E is simply a function of n times those claimed proportions, where n is the total sample size. The idea is, the key part of this statistic is what all you're doing, you see the sigma operator there, what you're doing is for each category, you're taking the difference between expected and observed counts, squaring that so it's positive, because you don't want these differences to cancel each other out, so you square that difference, then you divide by the expected counts. And then you add that quantity up, that sort of squared difference divided by the expected counts for each of the different categories. So that's all the sigma operator is doing. Remember, sigma, capital sigma, just refers to adding up these different values. And you add up whatever is after capital sigma. So in this case, we add up E minus O squared divided by E for each of the categories from I equal 1 to K. So if you have K equals 3 categories, you're going to have 3 terms. You're going to have E minus O squared divided by E for category 1, E minus O squared divided by E for category 2, and E minus O squared divided by E for category 3. That's all the chi-squared test statistic is really doing. When we work through an example, you'll see the sort of mechanics. The basic idea with this test statistic, similar to other test statistics we've talked about, is that when this test statistic is more extreme, to put it another way, when there's expected and observed counts, when that difference between E and O, when that's really large, the more inconsistent the data is with our null hypothesis. And when their data is inconsistent, that suggests that we should reject the null hypothesis. And formally, we compare that chi-square test statistic with some critical value. Right? That critical value lies on the chi-square distribution model. So what is the chi-square distribution model? Well, recall that the z-test statistic, right, we plot it on the standard normal distribution, which can be understood as a bunch of z-scores. Right? That's why sometimes the standard normal distribution can be called a z-distribution. Not that commonly, but it could be. Similarly, the t-test statistic, it's plotted on the t-distribution. Well, the chi-squared test statistic, it lies on the chi-squared distribution. So what is the chi-squared distribution? Well, it's a probability distribution, and it changes shape depending on the degrees of freedom. The degrees of freedom, if you recall, is simply the number of independent pieces of information that kind of goes into our calculation. For the chi-squared one-way goodness of fit test, the degrees of freedom is simply k minus 1, where k is the number of categories. So for our religion example, where k equals 3, the degrees of freedom is 2. Right? And that governs the kind of shape of the chi-squared distribution. An interesting property of the chi-squared distribution is that it ranges from 0 to positive infinity. You don't have negative values. The reason for that is if you look at how the chi-squared test statistic is calculated, right, you're taking expected minus observed counts, squaring them, divided by the expected cell counts for each category. You can't get a negative value from that calculation. So the chi-squared distribution, and accordingly the chi-squared test statistic, it can't be negative based on the calculation. And similarly, the chi-squared distribution is always 0 to positive infinity. It is a probability distribution, so you can kind of look at areas under the curve in terms of probabilities. So let's look at how the chi-squared distribution model really looks like. You can see that these are different degrees of freedom. Right? The degrees of freedom, again, in the one-way chi-square goodness of fit test is simply the number of categories minus 1. So you can see that this shape, in effect, of the chi-square distribution model, it changes depending on how many categories you have. The more categories you have, it kind of flattens out and looks a little bit more like the normal distribution. If you have very few categories, it looks almost like this sort of power law distribution. The important point here is that the underlying mechanics of what we're doing is similar to what we've done before. We calculate a test statistic and we put that on a probability distribution, and then we examine, how inconsistent our data is with the null hypothesis. So this is sort of a summary of the different varieties of the chi-squared distribution model. Again, it's a model of reality, but it's not reality itself. We use it to construct statistical inferences.